So we talked about linear acceleration and radial acceleration, right? Okay, last time. And we began all that stuff. So we really covered probably everything you need to know on page 1 and page 2. Okay? One quick thing, if you see an object of any kind, okay, this is the one that that gets students all the time, is, let's say you have a car, and the car is right here, all right? And it's moving this direction with a velocity, okay? But the velocity is constant, okay? So coming down the hill, the person had their foot on the brake. Going up the hill, they got their foot on the gas. They keep a constant speed. All right, is the car accelerating?
No.
Yeah, straight direction.
All right, now this is the thing that we all miss at this stage of physics. Because when we're thinking about acceleration, we think change in speed, right? Speed up, slow down, speed up, slow down. All right, but remember, there's change in speed, acceleration, and there's change in direction. And this is a constant trick question that gets students all the time at this stage because you're just not used to thinking of it that way. It is accelerating. It's accelerating because it's turning, and it's accelerating up. That's correct. All right, we're going to talk about that a little more in a minute. So anytime you have an object that is taking a curved path, it's accelerating. Now there's a dead giveaway that there has to be acceleration, all right? It's like, for instance, if you're running down the hallway and you need to turn, you know, running down one hallway because you're late, and you turn the corner to get into your classroom, all right? When you change directions, you don't just naturally change direction, right? If you don't apply a force to the ground to cause yourself to turn, you won't turn. You'll just keep going straight, right? Okay, every time that there is an acceleration, it comes with an associated force, all right? In order for you to accelerate, you must have a net force, okay? So think about it. Every time you're in a car and the car takes a turn, your body doesn't want to turn.
It moves. That's what we talked about in Paris.
Yeah. So here you go. I had a friend, actually, when I first began teaching, there was a veteran teacher, and she and her husband liked to play golf, okay? And so here's her husband, and here's her in the golf cart, okay? And they're driving along, and she's just looking out because it's a nice day. Well, a rabbit jumps out in front of the golf cart. And her husband takes a wicked left turn to avoid the rabbit.
She fall out.
Yes.
She hits the rabbit.
lands on the rabbit.
And it still dies.
Just about. Actually, she... Okay, in situations like this, we tend to say that the person was thrown from the vehicle.
No, it's the vehicle left the person.
Yeah. What happened is that the vehicle turned left. The driver of the vehicle turned left because he was hanging onto the steering wheel. Golf carts don't have seat belts, right? So he was hanging onto the steering wheel. So when he turned left, he hung onto the steering wheel and he went left with the vehicle. And the golf cart went left because when you turn the wheels left, there's friction between the road and the tires, giving a force causing the vehicle and the person driving to go left. Okay, she was the passenger. Didn't know what was going on. Wasn't holding on, so there wasn't enough friction between the vinyl seat and her seat to keep her, to cause her to turn. And so what did she do? She did what every object with mass does.
Remains in motion.
An object in motion stays in motion. And the vehicle left her behind. The vehicle ended up over here with her husband, and she went flying from the vehicle. Actually, the vehicle went flying out from underneath her, is what happened.
Wouldn't she kind of like be going?
Is she okay?
This
Yeah, she
way?
broke her hip,
Oh.
so she was in this big cast.
Oh,
Yeah.
Wouldn't she kind of
rabbit, and then
What's that?
In a perfect physics way, she would have like that, but wouldn't it be like this a little bit because there's friction between her butt and the seat?
Okay, now, if there's no friction at all between her butt and the seat, then she would just continue to go straight. Now, what happened is probably there was some friction, right? So she probably ended up over here somewhere, right? There was enough force to make her turn some, but not enough to keep her in the vehicle, right? Okay, this happens all the time. If you have anything that you can, that you want to make turn, anything on the end of a string, like a ball on the end of a string, and you're spinning that thing around, you're going to need something on the end of the string. Something on the end of the string.
That's a cord.
Yeah, that's a cord. All right, so you got this on the end of the string, you're spinning this around. All right? Okay, which way am I pulling on this cord?
Towards the center.
Yeah, I'm pulling this thing towards the center. That's the only way I can pull it, right? So it's coming towards the center. So when it's out here, it wants to go straight. In fact, here, I don't know how many of you have ever done this, as a child, the old-fashioned slingshot like this, and you want to try and hit somebody, So I try and, want to let go of this and make it go towards Juan in the back of the room. Okay, the very first time you try this as a kid, where do you let go?
At the front.
Yeah, you let go when it's right here, and where does it go?
That way.
It goes that way, and breaks a window, right? So if I want to toss this all the way back to Juan in the back of the room, then where do I let go?
Right there.
There, there, there. When it's right out here, because when it's right out here, it's traveling in that direction, right? So if I let go there, then it would go to the back of the room. So let's see.
Let's see.
You got to right. I let go. Tell me when.
There.
Right
There.
there. You're not remember.
Let go.
There.
Ian's going. Bad place to sit. Bad place to sit. All right. Get a bit closer. I did this. I used to have like a tennis ball on the end of a string, and I'd spin it around. I was spinning it around like this. Okay. Spinning around like this. Okay, where is it most likely to break the string?
At the bottom.
Why?
Just grab it. More force pulling down to tension.
Okay, because look, when you have this ball on the end of a string, there's a couple of reasons why it would be at the bottom. Okay? First of all, at the top, which way is the string pulling it?
Downward.
Down. And are there any other forces on the ball when it's at the top?
Tension going down.
Ooh, there's tension and there's weight, right?
Yeah.
Both these things are working together to pull it
There's
downward.
nothing pulling apart.
Okay, so these two are pulling down. They work together to make it turn downward. Okay? Now, right down here at the bottom, what do I got? I got a tension going up and, but the weight's going down. So the tension in the string, in this case, is not only has to pull it around the turn, but has to fight gravity in the process, right? So the tension is much greater at the bottom, okay? Much greater at the bottom. You've been in a roller coaster, right? A roller coaster that does a loop.
Yeah.
Where is it that you, when you go through the loop, that you experience the greatest forces? Not the top.
The bottom.
On the side.
It's at the bottom. Because at the bottom, this thing is pulling you up. The force on your seat is really great to make you go through this turn. It's fighting gravity and making you turn. Okay? That's where, okay, next time you go to Six Flags, okay, go on a loop roller coaster, hold your arms up. Okay? When you're at the top of the loop, no problem. But when you get to the bottom of the loop, your arms feel like they weigh like 30 pounds. And if your head's not in the right spot when you reach the bottom, you're like, you can't lift your head off your chest, right? Feel like you're like a little baby, all right? And if you're going to black out, where are you going to black out?
Bottom.
And why do you black out at the bottom? Because,
all the
All
blood
the force on
down.
you.
now is it pulling your blood down?
Well, no,
Pushing.
it's pushing you.
Yeah,
up.
what's happening is it's pushing you up, and your blood has a lot of mass because it's liquid. It's made of water. And so what happens is your blood stays in place as your body gets pushed up. So your blood doesn't really rush to your feet. Your body rushes up as your blood stays put. And it drains out your brain. And that's why you tend to black out at the bottom. How many of you have ever blacked out? Or the edges of your vision start to go dark and you get that like sparkly look in you?
Well, I've done that. I've never actually blacked out totally though.
Yeah, you kind of go, whoa, and your vision kind of starts to dim out.
Next time I was at Six Flags, I do the biggest net house to a random person I don't know and explain it to them. Like, like.
Oh.
So they would
Alright.
ruin their day.
Yeah, so Kennedy,
Yes.
do, we'll go ride roller coasters. A little bird told me that roller coasters are no good. See, it's perfectly safe. That's all right.
You're the bird, Lisa.
Oh, She's the bird.
The bird's the
All right. So
Oh, goodness, no.
when you spin something like this, the cord is most likely to break at the bottom. And I had that one year. I had like a tennis ball on the end of a string, and I was spinning it like this. And I was like this, and where did it break? At the bottom. And where did it go?
Forward.
Right out into the middle of class. Luckily, I was standing in between the students, and it went zinging all the way back to the back wall.
I was the bird
It was
with
a
the
tennis ball. I wouldn't have left a mark. Whatever. All right. Also, let's make something perfectly clear. Okay, when we're in a car and somebody takes a turn and you get flown towards the door and then you're pushed against the door, okay, you're not really pushed against the door. Okay? What's really happening is that you're in the vehicle trying to go straight and the car is moving.
The door's pushing you.
And the door is pushing you around the turn. Okay, we tend to think of this thing called centrifugal force that pushes you to the outside. That's not really true. What really happens, like on those rides at Six Flags that spin you around like this, okay? Like here. Actually, this one will be at the State Fair. You know the ride at the State Fair? It's the big drum where you stand in it and it spins and you get stuck to the wall and then the floor drops out.
Yeah.
Yeah.
Marcos, we didn't ride that one.
All right.
If you go in upside down, you stay upside down to the end of your ride.
Yes.
Fall in your hair.
Do they let you upside down?
Well, they don't watch you.
Well, that's true. The carnies are probably not watching.
Yeah,
are
I'm
they?
totally trying to stand hard.
I go sideways.
Yeah.
It would be hard though because there's so much torque force, like gravity, you know, pulling.
Yeah, you'll have people that'll get in there, and when it starts to go, they'll like to try and rearrange themselves on the wall. So yeah, you can lay on the wall sideways and stuff. If you look at it from the top, if you look at it from the top, what's happening is you're here trying to go straight, and the wall is pushing you around the turn to go this way. Okay? Because you don't want to go this way. Your velocity tells you to go that way. Okay? So it's the force from the wall causing you to take this path. All right? Now, that's how at least the old-time washing machines work. The newer washing machines that are vertical, that rotate like this, are not exactly this way. But the washing machines that are like this, your clothes are inside and it's filled with water and it agitates and washes them. And then the spin cycle is where it gets rid of the water. Because this drum is filled with holes all the way around. And so what happens is, as this thing spins around, the clothes get stuck against the wall and pushed around the turn. But the water can fit through the holes. So the water spins out like this and flings out tangent to the path as the clothes get squished against the side and get wrung out. So anyway, you can try that, by the way. Get like a big fuzzy ball or a tennis ball or something and dip it in water and then spin it. Throw it in the air and spin it. And the water will spin off tangent to the sides of the balls it spins around. How many of you ever ridden a bicycle in the rain? Anyone?
The ice.
You get a nice strip of mud on your back as the back wheel spins around. Because you're sitting here as you ride.
That's why the back normally has a covering over it.
Yeah, the back wheel normally has a fairing because otherwise what happens is
That'd be
I
funny.
bike
Good
on
shot.
this thing sprays you as it comes around. It picks up the water and sprays you right in the back of the head and down your back. If you don't have a fairing on the back, you'll end up with a strip of mud, muddy water right down your back.
I've never seen that.
You've never seen that? Well, there you go.
Do it.
Yet another reason to ride a bicycle in the rain.
Get a
All right,
reverse skunk.
you're a reverse skunk. All right, so let's make sure we get the mechanics of all this down. The thing you're looking for, everybody, and the thing that students miss historically on the exam is the fact that anytime you change direction, you are Accelerating. Okay? Now, the direction you are accelerating is the direction of the force. All right? And because that's F equals ma, correct? So the force is toward the center. Therefore, the acceleration is towards the center as well. All right? And that seems weird, but anytime you're changing direction, you're accelerating towards the center. Okay? So let's get this stuff out of the way. A little terminology. Let's go back to our sun and our planet.
Oh my God, you dropped it.
All right? Okay, if they ask you in this problem, they ask you draw the velocity vector. Which way would you draw it? Draw it.
Tangent to the.
What was the center of the sun?
No.
Well, it depends on what direction.
Velocity?
It's traveling
Tangent.
first.
Okay,
Yeah.
let's say that it's traveling this way around. So velocity would be this way, right? Tangent to the path. Okay, which way is the force on the planet?
Towards the
Towards the center. Force of gravity. So which way is the object accelerating?
towards the center.
Towards the center.
Yeah, F equals ma, right? F equals ma, so you've got to be accelerating towards the center. Now, this acceleration towards the center, again, is called centripetal acceleration. Okay, so let me write that down.
Okay, so you're saying the force towards the center is called centripetal.
It's actually going.
The acceleration towards the center is called the centripetal acceleration. The sum of the forces towards the center is called the centripetal force. Now, I want you to notice, please, that there is no new magical force that causes something to go in a circle. It's just the types of forces we've already studied, like friction, gravity, tension, normal, whatever, okay? Whatever those forces are, those are the things that add up to be the centripetal force, okay? There's not a new magical force called centripetal force. Does that make sense?
Yeah.
So when you draw free body diagrams, here, let's go back. That ride at the fair, okay? Here's the person stuck against the wall as this thing spins around. Okay, what are the forces on this person? Okay, well, there's certainly the normal force, right? Which way is the normal force?
Horizontal.
Towards the center, right? Because it's a contact force with the wall, always perpendicular with the wall. Okay, what other forces are acting on the person? There's got to be gravity, right?
There's friction.
There's got to be gravity, mg, and so Nia asked, is there friction? Would there be friction?
Yeah.
Does there need to be friction? What would happen if there was no friction?
You fall down.
You'd slide down the wall, right? So which way is friction?
Up.
Friction's got to be up. And if the ride is operating properly when the floor drops out, what can you say about friction and the mg force? Those must be equal. So look, we have an unbalanced force towards the center. That unbalanced force towards the center is the centripetal force. Now, on the free body diagram, if you write centripetal force right there, guess how many points you get?
None.
None.
-1.
Because they might take extra points off just out of spite. Because there is no such thing as the magical centripetal force that causes you to go in a circle. It's just a regular force. They give it the name centripetal, just so that you know what we're talking about. It's causing you to go in a circle. So this is the force that causes you to go in a circle. The normal force. Okay? So, and that is what causes you to have your centripetal acceleration. So the sum of the forces equals ma towards the center. My normal force is causing me to go around the circle. That's the mass of the person. And there's the centripetal acceleration. That's all there is to it. Okay? Not a big deal. The key thing is to spot that the object is changing direction. Therefore, there must be a force towards the center. A net force. Okay? Anytime it changes direction. If we were down in this location here, then the velocity would be to the left. The gravity force is still towards the center, and the acceleration is still toward the center. Okay? All right, here's a trick question. Okay? How much work does the sun do from here to here?
Yeah. Wait, from where to where?
From here to here.
Oh.
Well, is it a perfect orbit?
Yeah,
Is
It's in a
is it
circular
change-
orbit.
None, because it doesn't technically change position.
All right. There's a couple of ways to reason it. Remember that work equals the change in energy. If it has the same velocity, it also has the same radius from the sun, right? So is any of the energy changing?
No.
Okay, so that's not changing, so the work equals 0. Another way to say is, look, work equals F d cosine theta. Which way is this object displacing? It's displacing this direction right now at this instant. And which way is the force? This way. So what's the angle in between? 90. What's the cosine of 90?
Sorry.
Sorry, I'm having a problem.
Hey, at least nobody said pi, so we got that going for us.
Pi squared.
It's 0. So there's no work done. Now, that seems kind of odd because the sun is doing something, right? It's causing the planet to go in a circular orbit. But is that called work?
No.
No, it's doing something, but it's not doing any work, right? The energy's not changing. Very good.
Have you heard that?
I just got a raise.
Ah, that was funny.
All right, centripetal acceleration. There is a special way to calculate this, and it is, you ready? You ready?
Yeah.
V squared over R, where V is the instantaneous velocity and R is the instantaneous radius, the radius at that instant in time. Now, if it's uniform circular motion, meaning that it goes in the same, in a circle, a perfect circle at a constant speed, then the the speed will be constant and the radius will be constant. And so the acceleration will be constant.
So for centripetal acceleration, let's say it's an oval, you would just get the radius at that
Very
point.
nice. So what happens is if you don't have a circular orbit, say it's an oval, so it goes like this, all right? Then what you would end up with is at this point in time, there is a radius associated with this curve right here. Okay? So the instantaneous radius and the instantaneous velocity would give you the instantaneous centripetal acceleration.
And the radius wouldn't be from like the center of the oval, it'd be from the center of the thing pulling, right? The sun.
It would be this from the center of the geometric circle. All right? Of
so
the arc.
So not from the sun, but from.
Yes, for an oval, because that's not the center of this oval arc right
So
there.
the
Does that make
radius would
sense?
just be in this. Yeah.
Another example would be if something is in a parabolic arc like this, all right? Right here you have a certain radius, and then right here you have a much tighter radius, right? Right here at the top. When the velocity right here is tangent to the path and the acceleration is down right there, at this one instant during the parabolic arc, that is the centripetal acceleration at that one point. Okay? But when you're over here, g is this way, and so it breaks into components. This component is your centripetal, this component is your tangential or parallel to the path. Okay? Does that make sense?
Yes.
All right. Now, the nice thing is that in Physics B, since we're just learning circular motion,
It's on the circle.
it's all in a uniform circle. And if it's not in a uniform circle, it will be easy enough for you to reason out without, there won't be any numbers associated with it. Let me put it that way. Okay? So all of the stuff that we'll do will be uniform circular motion with one exception, but we'll talk about that one exception that you might see. All right? All right. So, what's very important for us then is to figure out the velocity, technically the speed, but the velocity of the object as it goes around in a circle. Okay? So, what's velocity again? Change in time. All right, now tell me this. That's like how far it travels in time, right?
But in this one, it's basically speed, though, right? Not.
Yes.
So you'd be getting.
The way
area
we're
of the
discussing
circle.
it in this class, it's really speed, okay? Now, when we get to physics C and we get a little bit more into it, then yes, it will be the instantaneous velocity.
So we'll get the area around the curve, right? Not the distance.
Well, that was going to be my question. When this, like for instance, how do we figure out the speed of the Earth? This is the Earth, okay?
You get the circumference divided by the year.
All right, yeah, this is the circumference, which is the 2 pi r over the time period it takes to go around the circle, okay?
Speedometer.
On the Earth, big speedometer.
That'd be,
Is that also located in Greenwich, England?
But I mean, doesn't this speedometer work by how much the wheels turn?
So you put a big wheel on there.
Yeah.
All right, so 2 pi r is the circumference, t is the time period, not temperature this time. All right, and that will tell you how fast something is going in a circle. All right, now, don't forget, time period. How is that related to frequency? 1 over the frequency, right? So you could write this as 2 pi r frequency. Okay, that's a possibility. So, 2 pi r over time period, or 2 pi r circumference times frequency.
if
All right?
that velocity, well, we're assuming we're in constant velocity, right?
Yes. Now, there will be a problem where we won't have a constant velocity. We'll talk about that
So it can't be
particular one.
2 pi r.
So here you go. If something is changing direction, if changing direction, then centripetal acceleration and a centripetal force of some kind, which means that you'll always have F equals ma towards the center will equal this, but we always know that this centripetal acceleration will be mv squared over r. So we're going to end up with this equation over and over and over again whenever we have something changing direction. Okay? All right. So now all we have to do essentially is identify objects that are going in a circle of some kind, identify where the center of the circle is. Now all you do is draw a free body diagram and set up your new type of F equals ma. This is just F equals ma towards the center. And it's going to look like that. Okay? So there are 3 varieties of this type of problem that you're going to run into essentially. All right? Actually, we have 2 of them right here. And so let's work with these 2 right now. Variety number 1 is where you have just a single force towards the center, and it's really easy to set these up. So, I have a planet going in a circle. So I'm going to set up F equals ma towards the center. So here we go. F equals ma. All right, first you draw your free body diagram. Okay, my free body diagram for the planet looks like this. Gravity. Gravity. That's it, right? Okay. Is it going in a curve, circular path?
Yes.
Yes, so I put a little C here to remind me of that. Okay, what are the forces towards the center?
Gravity.
Gravity. What do I put in for this?
E squared.
V squared over R. Can I do better than that?
You can solve for v if you like.
Well,
You can do better.
well,
Stop right now.
What's that?
MG.
And
That number.
no, it's
Ooh, is that mg?
no, it's g times m1 over
Ah,
r squared.
so this becomes big G, m1, m2 over r squared equals mv squared over r. Now I got a whole lot of m's and r's going on here, but let me make sure.
Yeah, 'cause
Somebody explain to me why I dropped the negative that's in this equation.
Because we're doing magnitude.
Yeah, because that just tells us it pulls inward, and I already have that taken into account by the direction here, right? So I already know that that's towards the center. So I got an M1 and an M2 and an M. So these 2 M's, what are those?
Mass of the planet.
One's the Earth and one's the Sun, right? So this one, which one is that?
Mass sun.
Earth.
Oh yeah, Earth.
That's the one going in the circle, right? So that's the Earth. So the mass of the Earth goes away. Interesting.
And one of the.
Ah, and this radius here, that's this radius, and this radius is the same radius, so one of the r's goes away. Now look what that gives you. velocity of a circular orbit equals big G, and I'm going to put big M over R square root. Now the reason why I put big G and big R, because big M, to remind you that we're talking about the mass in the center, right? The one that's being orbited. Okay, by the way, why doesn't the sun orbit us? Why do we orbit the sun?
It's gotta
It's
be.
heavier.
It's
Because the force on the two of them is the same, right?
But the masses.
But the masses are much
So
different.
accelerations are different.
So our acceleration is much greater than the sun's. Actually, the sun does wobble because of us. But it's so small that we don't really notice it unless you're really trying to measure it. Okay? All right. So big R, just for that being, usually big R means a distinctive radius, and that's the radius between the planet and the sun, instead of just some arbitrary radius. All right? You will need to be able to derive this. Just like you're going to have to remember how to derive this, don't forget that the force of gravity equals the force of gravity. Your weight equals the force of gravity, right? So that's mg equals big G, big M, little m over r squared, right? Where this is the mass of you and you go away. So g, the acceleration due to gravity, is big G, big M over the radius of the Earth squared, right? Don't forget that. Because our next test is going to cover everything we've covered. So it's going to have some energy in it. It's going to have some kinematics in it. It's going to have some gravity stuff in it. I don't know if I put any thermo on this one or not, but there'll be certainly all of mechanics, because we are at the very end of mechanics. We're almost done. All right?
Good day to you, sir.
All right. So, sit down, you. All right, so there we go. Hey, let's apply circular motion to this one. Okay, will you, first of all, you got to decide, is the object changing direction? Where's the center? Here. So my circle is like this, right? Okay, so then you can write F equals MA towards the center, and you could write F equals MA not towards the center, or perpendicular to that direction, right? And this one is really easy, because in this up and down direction, are we accelerating?
No.
No. So this is going to be 0, which just tells us that the force of friction must equal mg, right?
Yes.
Okay, we know that must be true, otherwise you'd slide down the wall. Okay, so what's this one going to look like?
Yeah, FC is normal.
Yeah, it's just going to be the normal force equals mv squared over r, and then you're done. Where r would be the radius of that big rotating drum that you get in. All right? Piece of cake. They really can't make that problem much harder unless they gave you the diameter instead, right?
Feels in free
Oh
fall.
Do it with
no!
two.
How would we do that?
The whole thing is in free fall stop. If they gave you the diameter, you just divide it by 2 to get to the radius,
You're
right?
accelerating down the wall at this rate.
No.
Submersed in the Pacific Ocean.
Stop. All right.
They could do accelerating down the wall though, couldn't they?
Yeah.
Yeah, it would change.
Yeah, they could, but in physics B, probably not.
Probably.
It's
They're dumb.
pretty. It's kind of easy.
Okay.
Not bad.
How about this? Let's say we have a turntable of some kind, like a merry-go-round. So here's one of these merry-go-rounds. It's rotating about this spot right here, and you've got a little kid sitting on it right here. Okay? And they're just sitting there, smiling, having a good time.
And it all goes
Yeah.
wrong.
Okay, let's do this. Let's say that the radius of this thing, radius equals, how big is the radius of those things? About 3 meters, say? Okay, about 3 meters. How fast did that thing go around?
After you can push it. Think how fast
Assuming
that.
circular.
Let's say the time for it to make one revolution is 4 seconds.
Slow.
Is that too slow for you?
No.
No.
3 meters,
pretty
that's
fast.
large.
Actually, that's about right, because think about it. I mean, the kid's going around 1, 2, 3, 4. That's about right.
Yeah, that's that's 3 meters in radius.
That's going to be a really big merry-go-round. I mean, all right.
You want
That's
to
going to be
say
pretty
wet?
fast.
Yeah, that's
You said soft or wet?
All right, let's say the mass of the kid is 30 kilograms. Okay?
Solve for the force?
So that's my daughter. All right?
Solve for the force?
Okay, what I want to do is I want you to solve for the centripetal force. What's the centripetal force? How big is it?
The one, oh, well, MA, we have to go
About
there.
mv squared over r.
Maybe. Let's see. What is actually here? Tell me, what's the friction force? How about that? Wait.
Staying still.
Are we
on the-
assuming,
So they're not sliding?
yeah, they're not sliding?
We'll assume no slippage, that the child's butt has enough friction to stay put. So my daughter's wearing her sandpaper pants. Wow. And she's not going anywhere.
She's on the sandpaper merry-go-round. Yes.
That's right.
No,
She's wearing her
Velcro.
she's wearing her Velcro pants. There you go. Find the force of friction. Okay. What's the very first thing you do?
Draw your body diagram.
Draw a free body diagram. What's the second thing you do?
Acceleration.
Decide if it's accelerating. Now, new thing here. When you decide if it's accelerating, you're looking to see if it's changing direction, right?
Yes.
All right. And that tells you the direction of acceleration.
4 seconds to go around once.
4 seconds to go around once. That's correct. Look, a lot of you are kind of stuck,
I got it.
Yeah.
but calculate everything you can calculate.
Move it up.
Okay. Well, we know we're going in a circle, which means that V equals 2 pi r over t. We know we're going in a circle. That means we know this. Right? We know we got a forces problem, which means we have to draw a free body diagram. Right? So a free body diagram, what are the forces on Alina
Gravity
here?
downward.
Gravity down,
Normal upward. which is
Normal up.
equivalent to man.
Thingy toward the center.
and we need one towards the center, and that's friction, right? So in this case, our centripetal force happens to be just friction, right? So if we're going to solve this right here, we would say, well, look, it's only friction towards the center, and that's mv squared over r. But I need to know what v is, right?
2 pi r.
All right, so that's 2 pi r over 4 seconds. What is that, 4.7-ish?
Yeah.
Is that right? Is that right? Okay, so that's going to go in here. The radius we know, and we know m. So we get 30 kilograms. We get 4.7-ish squared, and we get a radius of 3 meters. So what's the friction force required? What do we get?
It was like 166.
I got it.
Yeah, I
I got it.
166?
Something like that.
222?
I got 222.
Yeah.
All right, is 222 correct?
Yeah, Newton.
Oh, that's going to be right. This is roughly 5. 5 squared is 25 times 10. So yeah, 222 looks better. 222 what?
Newtons.
Newtons.
222 Gerbil. Anything.
All right, so if Alina is not able to hold on with 222 newtons, or friction is not as great as 222 newtons, then Alina gets slung off the merry-go-round, right? Okay, quick question then. What's the minimum coefficient of friction so Alina doesn't fly off?
Whoa. Okay, alright.
mg times that equals...
Yeah, so divide by mg.
Because all you have to do is say, look, it's going to be static friction though, right?
Oh, so it's less than 8.
So it's
But it's
mu
minimum,
force
so far.
normal.
Yeah.
But that's mu, in our case, just mg, right? Now, are we okay with putting an equal sign in if we're asking for the minimum coefficient of friction?
Yeah.
Yeah, because we're trying to, we're at the equal sign here. So all we have to do is divide that by mg, right? So mu equals 222 divided by 30 times 9.8.
Yes.
What do we get?
0.755.
Whoa, 0.755. She better be wearing her sandpaper pants because you're going to fly off. That's a pretty high
That's
coefficient
why
of
they
friction.
have bars.
Yeah, that's why they have bars on those things, because you get those things spinning pretty quick, and a child will go flinging off of that thing. Here we go! Texas Motor Speedway. Now,
Oh my gosh!
quiet, 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 back here. All right, if you're on a road and this is your car, you're looking at it from the back side.
Looks like the cow.
Looks like one of those block cows.
No, here's the back window. It's your Hummer.
What do you
Back
look
with
like
the
now?
There's your antenna.
No.
To the side?
It's on the front.
It's a
Look at
crappy
it behind.
antenna.
Behind. It's going straight into the wall.
No.
Why would he
Wow.
drive into a wall? Is Christy
Yes.
driving?
But you're going around in a circle. Okay, so you're going in three-dimensional. So you're going around like this. Okay.
Yes, you're right.
Yes, it's the
What
cow.
do you look like now?
You're drawing a cow riding in a circle.
Stop.
Is it skateboarding in a circle?
That's right. We have our spherical cow going in a circle.
It's a block cow.
Just bring it up.
Cow.
What are you doing?
Dynamite.
You guys are so silly.
What are you doing?
He's gonna draw
I
a
am so confused.
vertical
What was
slot
that
now.
thing that was hanging off of it? The tail.
At least you
So
didn't draw a
there's the
vertical
tail end of the
slot.
cow.
You think you know me, but you don't.
Oh,
Yeah, at least you
There he
didn't
is.
draw a vertical.
It's going in a circle.
Yes. Okay,
On
so
a
our cow
skateboard.
is going in a circle. You know we're taping this, dudes. So we got our car going in a circle.
Cow.
That's right. We got a cow car
A
going in a
cow
circle.
with a window on it?
Shush. It's going in a circle. Okay. What are the forces on the
Gravity.
car? Gravity.
Normal force.
Normal.
That's the only thing I ever know.
And
And whatever it's causing.
friction says it's a car.
Yeah.
Okay. Now the car is going in a circle, right?
Friction.
So there must be a magical force towards the center. That magical force is.
Friction.
Now it is a centripetal force, but we don't call it centripetal force. We call it what the real force is. Okay. It's not a spring force, right?
Well,
It's not tension.
It's not gravity.
unless you were like cool like
Okay.
that.
What could it be?
Friction.
Friction.
Are you sure it's not Chuck Norris swinging it around?
All right, now, shush. If you don't believe that, the next time we have an ice storm, get out in a car,
Turn.
get going, and turn your wheel.
That's how that ends.
Why?
On a bridge.
When you go at night,
Yeah, on a bridge in traffic. Now, when you do that, when you turn your wheel, you're not going to have enough friction to cause you to go in that turn you want to go in, right?
You're gonna lose a little bit.
Now, at Texas Motor Speedway, though, they don't just do this because we realize pretty quickly that there's not going to be enough friction for us to turn very quickly because we run out of frictional force and we can't go around the turn. So the way they get you to go around and turn more is they have a banked turn, and the car sits like this. Ooh, those are really tall tires.
Let's see. Let's see.
All right.
Bless you.
You-
That's
All right.
a crappy race car.
I know.
Not very good for people.
Yeah,
got
it's
bad
a
aerodynamics.
box. You'd like.
It's a bad cow.
Well, if it's a bad
But they also like.
Is it going slanted?
Yeah,
Yeah,
Stretch what out?
Texas Motor Speedway. The cow goes.
Well, okay, good point. Hey,
frictional force for
listen up. If there's not enough friction for you to go around the turn, then designers of roads,
Well, add the friction.
well, they can do two things.
They could put spikes down. More friction.
Number one is they could try to add more friction, but they can only add so much friction, right?
Sandpaper.
Like, for instance, the concrete highways have grooves in them. The grooves are to keep the water from puddling on the top, thereby making sure you have a sizable amount of friction at all times, right? If you take a turn on an asphalt road, you're much more likely to slide than you are on a concrete road in general, especially with the concrete has these grooves. because the grooves add friction, right? Where asphalt is smooth, and you're much more likely to slide, okay? The other thing you can do is they can make the turn not so narrow. They can make a wide radius turn. Okay, look, when you're in a neighborhood, you come to a stop sign, you stop, look both ways, and then you step on the gas and turn, right? And so you can make a really tight turn because your velocity is very tiny.
So friction.
Because look, force of friction equals mv squared over r, and this, your limiting condition is when you have mu mg, right? And so what happens is if your velocity is too great, you can't get enough friction, right? Or if your radius is too small, that also makes this number really big, right? So in a neighborhood, you're going a really small velocity, so your radius can be really small and your acceleration's not that great, right? No big deal. But they certainly on a highway don't make turns like this, right?
I don't want to kill
Not on the interstate, right? Because you can't make that turn.
They can.
You just use both lanes.
You can't.
You use both lanes.
You can.
You start
can.
all the way
That's
around.
great.
You use the whole highway.
Man, I
and
fear for the world.
Only
when they get
if
their
you
license.
slow down enough.
Everybody slows down.
Right. Only if you slow down.
Speed.
Now, you can drive like that to increase the radius, right?
But it's still not.
But on a highway, that's not enough. So on a highway, they make the turns very gradual, okay? Because you're going at a very high speed. The other thing they do is they bank the turn. Now, why is banking the turn going to help?
Because it's just a normal force in the x direction.
Because you end up with gravity, and you end up with normal force, and then you still have friction. Actually, what happens is they design these highways so that no friction at all is required for you to go around the turn.
So you can have no wheels.
Actually, you can have ice on the highway, and yet the design speed of the turn, you can make the turn with no friction whatsoever.
But nobody follows the speed.
Not all of them. Well, that 175, you have to slow down a lot, but that one you do need friction.
Now, if you're beyond the design speed of it, then friction's required. Look, here's the
Well, not
deal.
even that. It's almost,
Rudy,
it's like 100.
okay, what happens is this is going to be a little different, so pay attention. Normally on a problem like this, we would say, okay, here's our object, and we would say, draw the forces, and we'd have mg, and we'd have normal force. And if there was no friction, that would be it. Then we'd say, okay, next question, is it accelerating? You'd say yes, and you'd say accelerating this way. So you'd set up your coordinate system like this, right? Okay, but this time, when you're going around this turn, think three-dimensional. Is the object accelerating?
Towards the center.
Yeah, but this time it's not accelerating this way. It's accelerating towards the center. It has a centripetal acceleration. So now, how do we set up our coordinate system this time?
Standard XY.
A standard XY. Okay? Well, yeah, we just make this positive because it's more convenient, right? This is different because now we're accelerating towards the center of our circle, right? We're not sliding down. We're accelerating towards the center of the circle, all right? Now look, this means that you can actually go around this turn without any friction whatsoever because you would split this one up this way. Notice I'm not splitting up mg because it's in the y direction. But normal force is in the y and x direction. So I take this and I split it up into two components. The component towards the center and the component vertical. Okay, now, everybody, the sum of the forces in the x equals ma. What's this going to look like?
X, we just have the, what is that, cosine?
All right, if this is theta, that makes this theta.
That's cosine. F something cosine.
Sun.
Wait, which one are we looking at? Oh yeah, up, yes.
So this is my x direction, this is my x component. So that's going to be normal force sine theta. That's it. Equals m
AC.
AC. This is centripetal, so that's v squared over r. So there's our equation in the central direction. Everybody catch that? Because we're accelerating this way. We only have this one force in that direction,
So we
this
have to
component.
accelerate in that direction.
So we have to accelerate in this direction if we're going around a turn. Okay? So what does this look like? F equals ma in the vertical, y direction.
Well, it's not accelerating.
F and cosine theta and
Gravity.
minus mg equals
0.
0. Why does it equal 0?
You're not accelerating enough for
You're
gravity.
not accelerating. Or most students will skip this step and they'll go straight to the normal force cosine theta equals mg. All right? Now notice we have no friction. All right?
We
I'm sorry. Yeah, we set it up with no friction.
If we did, we just added into it.
Yeah, if we have friction, it turns out to be a harder problem, and I'll show you in just a minute why. Okay, look. I want to know what this velocity is. Okay? If the radius is given, and the mass of the car is given, and the angle is given, I don't know what the normal force is, but I'm looking for the velocity. So I have two equations and two unknowns. Look what I'm going to do. And I take this normal force, and that equals mg over cosine theta. And I'm going to sub it in here. Look what I get. I get mg sine theta over cosine theta equals mv squared over r. All right, what happens?
Mass is cancel out, and then sine of. You can do sine of cosine tangent if you want.
Yeah, so I get a g tangent theta equals v squared over r. Or I can solve it forever I want, right? Okay, the important thing is that the design speed of this turn depends only on the radius and the bank angle, right? Okay? And of course that we're on Earth, right? Acceleration due to gravity on Earth. Notice that the mass of the vehicle makes no difference. So if we have a dump truck or if we have a motorcycle, it makes no difference. It's going to be the same bank angle for the same radius turn to give you the design speed, okay, of that turn, so that you wouldn't need any friction.
So if we had friction though, there's another component.
All right, so let's say,
Normal.
first of all, if you're driving too fast, actually no, let's go the other extreme. Let's say that you're not driving at all. You stop on the incline. So you're going around the turn and you just stop. All right? Which way does friction need to be then? So you
That way.
that way, because you're in this, you're right here then, right? Because if you stop, you're no longer accelerating towards the center, and you would want to slide this way. So friction's going to be this way. So if you go too slow, friction will keep you from sliding down the incline. Okay, so more likely, what happens? You go too fast. If you go too fast around a turn, then which way does friction need to be to get you to go around the turn? This way. But it's going to be this direction.
With X and Y.
Yeah, so you have X and Y components, and so it ends up being a combination of a couple things. This component of the normal force and this component of friction causes you to go around the circle to make the turn. All right? And then the normal force up here equals this part of friction and mg down. All right? That gets pretty complicated. If you can just at least draw the direction of the friction that's necessary, when you go around a turn, if you go too fast, it's towards the center. If you go too slow, it's out towards the outside or up the incline. Yeah, because this ends up being a pretty complicated mathematical problem. More complicated than you would reasonably be asked probably on an AP exam.
So they usually put the friction going that way?
Well, that's if it's too
That's if you're going too fast. If you're going on a frictionless surface, then this wouldn't exist at all. It's like they might ask, on a frictionless surface, at what speed could you make that turn?
No, but like in real life.
Oh, in real
You
life,
do have friction.
in real life you would have friction. So if you go too fast, friction will be this way. If you go too slow, friction will be that way.
If you actually make the turn.
If
which
you're
is why
at
if you go too
exactly
fast,
at it where it's normal, there's no friction.
And if you go at the exact
Forward,
speed right here,
it'd be tangential friction.
if you go at this speed, V equals GR tangent theta square root, that speed right there, then you will need no friction. Your tires will not, your tires will be rolling, but there will be no friction in order to get you to go around the turn. Okay?
But of course, in real life, you would have friction. So.
Well, he's just referring, you don't need friction.
There will
to
be no
keep you
lateral
from sliding.
friction, one way or the other.
Forward or backward.
Okay?
We always.
All right. That's a little bit complicated, right?
A little.
All right, so let's look at another one like this. What if you have, where's that, here it is. Okay? All right, take this thing. Oh, no, I'm not going to hit you, really. All right,
Too hard.
okay, look, if I spin it real slow, you're on the swings at Six Flags. Here you go.
Oh, I love that ride.
It's a fun ride. You're on the swings at Six Flags, so you're going around like this. Notice you got an angle, a droop angle. It's drooping downward, right? Okay, what happens if you spin it faster?
The land
Go higher. Angle
decreases.
gets
Angle gets smaller.
Well, it depends.
Can I make it go horizontal?
Of course.
Yeah.
Really?
Yes.
Okay, I want you to draw the free body diagram of a person in a swing at Six Flags. So here's the ride. Okay, here's the person on the swing.
Because
No.
you're only providing
Okay.
force horizontal. and
What are all the
weight-
forces on this person when they're going around the swing?
Gravity going downward, obviously.
Gravity
Going towards the center.
Tension.
and tension. Is that it?
Yeah.
And whenever you're going horizontal, it would just be
Okay.
tension. Without you can't make it.
Yeah.
go
If
up.
you were to go horizontal, what would it be like?
tension
you'd be
would
like
have to be
this,
going
right?
Down some.
And there would be tension this way, and there would be mg this
And we
way.
can't do that.
So.
Is that possible to do?
No.
No, because what's going to happen?
Unless you
This
have
one, this tension is causing you to go in the circle, so that's okay.
But then
But
you
what's
go
that
down.
mg going to do?
Then you go down.
That's going to
Never
make
gonna
you
be
accelerate
exactly
down.
horizontal.
So then you would so.
So you'll still end up at an angle. So why is it when you spin faster and faster that this angle gets smaller, but we know that it can't get to zero? It
Because
can't
the
go
tension
horizontal.
increases, so the y component of tension increases so
Yeah.
greatly.
But eventually, in
a lot of
horizontal,
gravity
there
out.
is no y component of tension, so it's nothing.
All right, because here's the deal. As you go around the circle, you need a bigger and bigger centripetal force towards the center if you're going to go faster, right? So if the only way that that's supplied is tension our centripetal force?
Yes.
Really?
The x component of tension.
Oh, there we go. The x component. This component right there, Tx, is our centripetal force, right? So if I gave you this angle right here, theta, okay, then it would look like this. The sum of the forces equals ma. Now wait a minute. Okay, there's our free body diagram. Is it accelerating, yes or no?
Yeah, to the center.
Towards the center. So I set up my coordinate system like this again, right? Towards the center and then perpendicular to that, right? So if I do this towards the center, what force goes in here?
Tension x.
Tension X equals mv squared over r.
Texas.
What's my tension X?
T sine.
T sine theta equals mv squared over r. There you go.
So Texas equals T sine theta.
Yes, in this case.
Okay.
Hey, what happens in the vertical direction? What do we know?
Sine of forces equals.
Yeah, that force and that force cancel out. So in the vertical direction, we know that mg equals
And cosine.
ty, or mg equals t
Cosine.
cosine theta, right? There you go. All right. And as you go around the circle, as the velocity increases, the tension must increase. Right? And as the tension gets bigger and bigger and bigger, look what happens. As this tension gets bigger and bigger and bigger, look, this vertical component is bigger than mg. So what does it do?
Accelerate.
It accelerates up. It accelerates up until the angle
It's so small.
is so small that the mg here is equal to this component here. And that's why the angle gets smaller and smaller and smaller. It gets more horizontal as you spin it faster and faster and faster. Because the tension is pulling in harder, and that's accelerating it up. Okay? But you can't get it exactly horizontal. You never can. All right?
Unless you have like a charge at the top or whatever.
Unless you have an extra force. All
Right.
right?
It's at the bottom of the person.
Sure. Now, if you were in space, with no mg, then yes, you could spin it horizontal. Actually, any angle you want. It wouldn't matter. All right? All right. Now, we've got one last situation for circular that we really want to talk about.
I'll be up 3 minutes today. Got time.
Excellent. 3 minutes is plenty of time.
You're gonna waste it, wasting the board.
Up 2 minutes.
Oh no, 2 minutes.
Up 1 minute.
Okay. There are two types. Well, it's a vertical circle, okay? This could be a ball on the end of a string, spinning it around, okay? Going around like that. It could be a roller coaster car, okay? Going around the circle. Or it could be a car going over the top of a hill, like this. Okay, these are both what we call inside circles. The forces are pushing them in towards the center, and the object has something around it pulling it in. All right? This is an outside circle where there's really nothing pulling it in except for gravity, which is just down. All right? So let's do this one first. Okay? Let's say that the radius of this hill is r. Let's say it's going at a velocity v. All right? And I want to figure out what the normal force is on the car. All right? So tell me, right here, what's all the forces on the car?
Just gravity down.
Okay, there's an mg, and there is a normal. All right, is the car accelerating?
Yeah.
Yes. Which way?
Downward.
Down. Towards the center, because it's changing direction. So it's accelerating down. Now, trick question. Does normal equal mg?
No. I guess not.
Normal equals mg, but you have an extra
No,
force.
because.
No, because well, you can't accelerate.
What's the extra force?
Yes.
Friction.
No,
Friction.
it's not.
Friction. Friction's pulling it down or pushing it up?
It is.
Wait, if
Wait.
you have
Normal is less than mg.
Friction has to be one of these ways, which won't help it in this direction.
So.
Normal is less
It's
than
moving towards the
So
center.
in, well, depending on.
N is
minus
less than-
mg.
No, it's the
mg.
same, but the direction.
MG plus MA.
I say
So is that
MG
the
is
I think it's the same
bigger.
because that's not
Mg
enough
is
force.
greater.
Okay, don't let your brain trick you. Are those the only two forces in this direction? There's no springs, there's no charges, there's nothing else, right? Okay, is it accelerating?
Yes.
Which way?
Down. So
Which one's bigger?
MG has
mg has to be bigger.
It's a lot.
The sum of the forces equals ma. It's just like when you're in an elevator, the normal force and your mg are not necessarily the same. If
Even
you're
though you're
accelerating
in
up, normal's bigger. If you're accelerating down, normal is less. When you're going towards the center, you're going to have mg minus the normal force equals mv squared, and we're out.
That's beautiful.
See ya!